Hello everyone, this is a review video for Quarter 2, Test 1, Ecology Lecture 2.7 through 2.9. So for 2.7, there are a few questions that I would like to go over with you, just in case you have a little confusion about it, and you didn't get to come to one of the review sessions. So the first question is question number 1, what is biotic potential? The thing about this question is that sometimes a student might answer a biotic potential is related to the amount of resources or natural disasters or the amount of competition in a population. That is incorrect because whenever we talk about biotic potential, we already assume that this is a perfect condition. How fast can a population grow at perfect condition? Or where you can say, what is the highest rate of population growth when the environmental condition is ideal, which means there is no competition, or there is very little competition. There's plenty of resources, plenty of space. The weather is great. There's no natural disasters. How fast can the population grow in that case, right? So when we think about an exponential growth, this is often happening and related to biotic potential because exponential growth can only happen when there's very little limiting factor that limits how fast the population can grow. So the population will just keep growing. So the second question says, is biotic potential the same for different population? That will be different because depending on how many offspring a certain animal or plant can have, right, that's going to influence how fast this population can grow. So for example, if you were to have a horse, within 1 year, the horse population's biotic potential might be a lot lower compared to a bacterial population because the horse doesn't reproduce as often, the horse doesn't reproduce as many offspring at a time. So this leads on to the next question, what are some factors that influence biotic potential? So you got to think about under ideal condition, what still makes different populations different in terms of how fast the population can grow. So one of them is the age of reproduction. So if you have an animal that doesn't mature for 10 years, that population is not going to grow as fast compared to a population that has animals that can, survive for 2 or 3 months before they can reproduce. So that's one factor. A second factor could be how many offspring that the organism can have at a time, right? How many babies can you have at a time? So that's going to influence how fast the population grows. Third one would be the overall lifespan of this organism, right? So if you have a longer lifespan, that allows you more likely to reproduce more times. So that will allow the population to grow faster. The last one is the number of reproductive periods. So this is kind of related to the last one, the lifespan. So this one is the number of reproductive period during the entire lifespan of an organism. So the more reproductive periods you have, the faster the population is going to grow under ideal condition. The next one is what is the difference between exponential growth and logistic growth? So it's important for you to know that exponential growth has very little or no limiting factor whatsoever, and logistic growth is, you start slow. Well, you start kind of slow, and then it goes very fast, very quickly. Let's take a look. A lot of markers. All right, so this marker. Second. All right, here we go. So if you were to have a graph that looks like this, that will be an exponential growth. But if you had a graph that looks like this, that will be a logistic growth, right? So logistic growth is when you have the first phase where the population grows really fast, and then the second stage where the population growth slows, and then the third stage where the population growth stops, right? So by the time you get to the third stage, the population could still be growing, but it grows a lot more slowly compared to the previous time. And the next one is what is the carrying capacity of a population? The carrying capacity will be whenever you get to this point where the population growth basically stops, that is the carrying capacity. Population crash, when population goes down really drastically. The age structure. Okay, so the age structure of a population is one of those pictures that we saw during class. So let me show you actually from here. Let's see. So this one right here will be an age structure, right? So there are two pieces of information here that you can see. One is the number of males and females at different age group, and the second one is how many overall population you have at each age group. So for this one, for example, we only separated the population into 3 age groups: the youngest 0 to 14, the middle age 15 to 44, and then 44 plus, 45 plus, right? So in this case, we look at these 3 age groups. How many individuals do you have in each of the age group, as well as how many males and females you have for each of the groups. So what does that tell you? It could tell you how fast the population can grow. If you have a lot of really young people, or the age group where individuals can be reproducing, or if you just see there are a lot of babies, that tells you that the population is growing really fast because a lot of offsprings are being produced, and then the amount of older people is a lot less. And then in this case, there's a slower growth in comparison to the first graph because you have less of the offsprings of the younger people within this population. So this is called an age structure because it tells you the structure of the age within the population. And then there's another one that's related. Actually, it's not on here. Okay, so the next one is 2 types of different reproductive strategies. You have the R strategy and you have the K strategy. The R strategy is, you can think about a fish. So a fish can have many offspring. Each of the offspring is very cheap. So what that means is that you put in a lot less energy into producing those offspring. So if you think about the fish eggs, right? The fish eggs are not very well developed. It doesn't take as long to allow a fish to reproduce, and you have a ton of those fish eggs. That is the R strategy. In comparison, you have the K strategy where the offspring is very expensive. For example, if you had a horse, the horse offspring is very expensive. It takes a long time for those horse offsprings to be made. These horse offsprings, you have very few of them, and it takes a long time. Did I just say that? They're expensive, it takes a long time, and you don't have as many. So that's the K strategy. The next one that has a little confusion for some people is the density dependent versus density independent limiting factor. So what those are is if you have a density dependent limiting factor, that means the factor itself and the result or the influence of the factor kind of have a direct correlation. So for example, if you have disease, right? The higher the population density, which means everybody's really crowded, the higher the disease, or the faster the disease is going to spread and kill off a lot of the individuals within the population. So if you think about it, right, these 2 factors, the density itself and the disease, they're directly related to each other, right? Another example could be overcrowdedness or the amount of resources. The more individuals you have within this area and the denser the population is, the faster they're going to get rid of the resources, and they won't have enough resources if the population is very dense, right? So this is related to density. If you had a density independent limiting factor, then this factor is going to affect all the population, whether you're a horse, whether you're, say horse a lot, you're a rabbit, you're a tree, it doesn't matter what you are, and it doesn't matter how crowded you are, if you have this factor, it's going to affect your population no matter what. Okay, so that's a density independent limiting factor. There are 2 ways that you can think about it. One is that it's usually a natural disaster because whether you want it or not, whether your population is dense or not, this density independent limiting factor, such as a hurricane, is going to affect you if you're in the way, right? So that's density independent. A second way to think about it is that if you have a factor that there's plenty of it, no matter what, that you could also call that density independent. So for example, the amount of nitrogen, that was on our quiz, the amount of nitrogen in the atmosphere is density independent because no matter how many individuals there are on the planet, there's going to be plenty of nitrogen just because there's so much nitrogen, right? So it's not really a limiting factor at all, first off, and it's density independent because it's not, the amount of nitrogen is not going to change by much, whether your population is dense or not. So that's density independent limiting factor. When we look at a graph like this, a logistic growth, the factor that allows the population growth to slow down is usually a density dependent limiting factor, right? The reason why this population grows really fast and then it slows down is because now that you have so many individuals within the population, there's not going to be enough resources, or the population, the disease is going to control how fast the population grows now. So then you have the population grows kind of plateaus, and the population size, so this should be population size, stays the same. Okay. The last one over here, people also have some questions about this. This is called 3 stages of demographic transition. So the 3 stages of demographic transition goes like this. You have high level of birth and death. So whenever you have a population, this is what you start with. Well, we're talking about people specifically. We have high level of birth and death. So if you think about the old days, right? High level of birth because animals naturally give birth. That's what animals do. As people, we're animals, we give birth. That's why we have high level of birth in the beginning. Then there's also high level of death because in the old days, the medicine is not as advanced. You don't have as good of a shelter, and there could be predators for humans. So all of those is going to cause high death. So at this high level birth and death, the population growth rate is not going to be very fast. And then we move on to the second stage. The population growth rate, the birth rate is still pretty high, and then the death rate kind of goes down a little bit. So this happens because people are getting better at surviving, but the mindset of let's not have so many babies have not caught up with this process. So now you have high birth and lower death. So in the second stage of the demographic transition, you'll have a pretty fast population growth rate. And then third stage is our low birth and low death, because by this point, the medical technology has gotten better. We've gotten better at surviving. We have shelters, food, everything is great. And then we have low birth because by this point, people think, why give birth when you can live a good life yourself, right? Or why have 8 children when you can just have 2? So some people do think that way. Nothing wrong with having 8 children, but overall, the population growth slows down because you have low birth and low death. Now, moving on to the next one, 2.8, I would say, well, everybody's pretty clear with primary versus secondary. One has soil, which is secondary. One doesn't have soil, which is primary. So for primary, you can have a glacier retreating as one of the causes of primary succession, or you can have volcanic eruption where the lava cover up the soil, right? Everything underneath the lava is going to be covered. So now we start on top of the lava, and that's called primary ecological succession. Because secondary succession has soil, within the soil you can have some roots and seeds, which allows the secondary succession process to happen faster. So a succession is the rebuilding process of an ecosystem after a major disruption to the ecosystem. Excuse me. And then, what is the difference between primary and secondary ecological succession? Which one can begin with some life? So this is question number 22. That has to be secondary, right? This is the case where you have the soil. There could be something under the soil that's not destroyed yet. Which one doesn't begin with soil? That will be primary. Which one usually starts in a new area? That will be primary. Which type of organisms are usually the pioneer species? So if you're talking about primary, that will be the lichens and the mosses, because they can grow on the rocks. After a while, they can help break down the rock, and the organism itself breaks down, which forms soil eventually. But that's what you start with. That's why we call it the pioneer species. They're the first one that enters the ecosystem and stays there. And then we have the secondary ecological succession. The pioneer species could be some grass, some small shrubs, certain trees if you have the roots already in the ground and it's not dead, right? That's great. And the last one, which one has a higher biomass, that should also be secondary. For 24, the first part of the question should be yes, and the second part of the question should be no.